Well, good morning, everybody. Welcome to our webinar on a day in the life of a Quarkus microservice. So today, I think we're going to have a look at how we can make our applications a bit more cloud native. We're going to work with Red Hat to also give us a nice overview of Quarkus before we get to the more technical side of things. So my name is Ben Taljaard. I'm a senior architect at Deva team in the Netherlands. I'm passionate about cloud-native applications. I've probably been working with OpenShift and microservices now for the last 2 years or so, and it's really something that I enjoy. I think before we maybe Ruud is also helping us today. Ruud, can you introduce yourself?
Yes, thank you, Ben. My name is Ruud Zwagenberg. I'm a solution architect with Red Hat. I have a background in systems development and integration, and I'm very, very passionate about microservices, about OpenShift, about Quarkus. Really love it. So I'm glad I can do this webinar today with Ben. And yeah, that's. I hope you all enjoy and learn something. Okay, Ben.
Thanks, Ruud. So Deva team has been a partner with Red Hat since 2016. So we are a premier partner in 9 EMEA countries. And we've got 250 plus specialized professionals with 150 plus certifications in EMEA. So with that, I think over to you, Ruud.
Mute.
Ruud?
Live broadcast, so sorry, get it on mute. So before we do a nice demonstration of Quarkus and microservice by Ben, we'll tell a little bit about the background of Quarkus. If you not know it, Quarkus is a what we call a Kubernetes native Java stack, specifically developed for Java application to make them cloud native, to make them better run in containers. And why did we do that? We found out that the traditional Java stacks are developed, 20, 30 years ago for systems with dedicated hardware, not cloud enabled, with plenty of hardware, plenty of RAM running on their own. So keeping them small was not a big deal. And also the most Java applications were started once, ran for entire days, maybe weeks, and starting and stopping was not a big deal, right? But this is not what we did. So now we're in the cloud world, and we're even looking at serverless. And now we found out that, hey, if you want to run your Java application in a container, then start the boot time. Well, it really does matter, and also the memory footprint really does matter. So a lot of people were looking at other languages than Java, and that's a bit of a pity because the whole Java community is quite large, right? So we thought at Red Hat, why don't we spend some time in making Java sexy again, right? Making it fast again. So we developed the Quarkus framework, and the major benefits are very reduced memory footprint. It starts way faster than the traditional workloads, the Java application, and it has also a smaller disk footprint. Now, okay, Ben, please next slide. Yeah, and to give you some little bit of details about what the results are, we did some tests. You can do it yourself, and we found out if we run Quarkus natively in a container, so natively built for a Linux operating system, it will start up in, milliseconds. If you compare that to a traditional stack, same code, same Java, if you do it on the traditional Java stack, It takes at least, 4-5 seconds. And if you make your application a little bit more complex, then the results are even larger. Then starting up a Java application would take you 10 seconds. Then normally that wouldn't be a problem, but if you want to do serverless, if you want to have containers and scale them easily up and down, 10 seconds is too much time, right? You can do serverless with applications that take 10 seconds to start. Okay, next slide again. So how do we do that? What is the magic? Normally, traditional runtimes, Java applications, we build them. We do not compile them for a specific platform. We only compile them for the JVM, and then we started on the platform of choice, on a JVM, can be any system, right? And then on boot time, a lot of things happens, right? Before the application is doing is running the business logic, there's a lot of things that are happening. So what we changed, Ben, can you do the next slide?
Yeah, sorry.
So what we changed, we do all the heavy lifting in the boot time, we do it in build time. So what we eventually produce with the Quarkus framework is not a class AR file. No, we actually produce a native image which can run perfectly in a container, and all the things you normally do at boot time we already did in build time. So it means that also building your takes somewhat longer. That's the offer you have to bring, right? Because it takes time to boot time takes time. But the big advantage is if you start your application, it's already pre-cooked, right? It's ready to go, and it will start in milliseconds. So besides that, a little bit of Red Hat. The Quarkus framework, we developed it a couple of years ago. We spent a lot of time to make it perfect. We released it last month, so you can have not only use it as a community utility, but also it's supported. It's part of our runtimes proposition, so you get full support for your Quarkus, and we're still spending a lot of time in making it better with all kinds of utilities and all kinds of yeah. So that's my piece of cake, my 15 cents. Ben, the floor is yours. Show the guys what you got.
Thanks, Ruud. So yes, for the next section, we're actually going to dive into a Quarkus real-world sort of scenario of a Quarkus application. But I think before jumping into the actual tech demo side of things, I need to give you a quick overview of what is required before we can actually release a microsystem into the wild. So there are these, how can I say, the cloud native capabilities surrounding a microservice, or that a microservice needs to support in some way or form. Now, this enables us to manage and observe and interact with our microservices in a consistent way within our ecosystem. So, yeah, microservices don't live in isolation, so they need to play well with others in your platform. So firstly, your service needs to expose some sort of API in order to communicate with other services or have other services call it. And this could be stuff like your REST endpoints, events. It could be some reactive application API that you build. But in essence, we need to expose some sort of service contract to the outside world. And this is something that you would do with Quarkus, for example, by doing a REST easy service, for example, or Vertex or something like that. Next, we need to also make sure that our microservice is discoverable. Now, when we deploy to a platform like Kubernetes, it actually keeps track of where your containers are running, what your endpoints are. So it does some sort of registry with discovery to pick up where your containers are running. We also need some way of calling other microservices. So Kubernetes provides you ways to, on a networking level, to actually invoke other services. So it provides the SDN so that you can interact with services. Your service also needs the ability to scale. And now, once again, a platform like Kubernetes provides components that allow you to scale up your containers based on load. It also makes sure that you can maintain a consistent set of containers of your application. Looking at resilience, there are multiple angles here. I mean, there's one from a platform level and from an application level. So on a platform level, of course, your Kubernetes infrastructure makes sure that your containers are actually running. It also needs health checks, or it does health checks to know if it needs to restart your containers or if it's actually ready to accept requests. And on an application level, we can also implement patterns like circuit breakers, bulkheads, or timeouts to make sure that our application is a bit more resilient to failure. And this is going to be one of the areas that we are focusing on our demo today. Once we are ready to release our code, we need some sort of pipeline. Now, a platform like OpenShift, for example, adds source to image or some pipeline capability that you can actually automate your process of release. When we look at authorization and authentication, your application needs to make sure that the consumer of a service is who they say they are, essentially, and that they've got the correct permissions or access to data that they require. Now, there are multiple different ways of doing this, but the important thing is that Quarkus also supports authentication methods to make sure that you can essentially annotate your code to make sure that you maintain the security. For logging, we can't really store logs inside a container. Containers tend to come and go, so we need infrastructure to go and scrape logs from your applications and aggregate that in a consistent way. OpenShift uses Elastic, Fluentd, and Kibana to go and scrape that from your containers. So this is typically a platform function, not an application function. For monitoring, we also need to make sure that we can observe what happens in our service. So, for example, we need to expose stuff like metrics that we can collect in tools like Prometheus and Dashboard in Grafana. Now, Quarkus implements the microprofile metrics, so it essentially exposes that in a format for Prometheus to pick up. Now, finally, our applications, microservices in general, form part of a distributed application. So in order to see what's happening between our microservices, we need to implement some sort of tracing. Now, once again, Quarkus has implemented the microprofile open tracing standard, and that's compatible essentially with tools like Jaeger, so that you can actually see the tracing within a nice dashboard, like a stack trace, call it that. Now, with that in mind, I just need to let you know all the code that we are looking at today is on my GitHub account. It's just Ben Tyler at GitHub, and there's a cool store Quarkus repo. As the name gave it away a little bit, for this demo scenario, typically Red Hat used a cool store example for their microservices to show polyglot implementations and all sorts of stuff like that. So I've decided to rewrite 3 services in Quarkus to see how that would look like. So it's a nice real-world example. So I've only focused on 3 of the services. Essentially, we've got a catalog service, which stores all your products for your cool store, and that connects with a MongoDB data store. There's also an inventory service connecting to Postgres that stores product availability, so how much of a certain product is available and where. And then we've got a gateway service, which essentially implements the microservice pattern of an API gateway. Or integration terms, it's essentially an enrichment service where we enrich our product information with its availability. So there's a new API that has that enriched capabilities. Okay, so let me show you what I've got. So I've got 3 services available. Let's start with our product catalog. So first, I've implemented a bare bones implementation of these services to show the concepts essentially. Looking at a data model, what is quite nice in Quarkus, I found, is that they've got these Panache libraries to interact with your databases or data stores. In this case, I'm using this Panache Mongo extension. And this allows you to have a very simple definition for your model. Essentially, just define your field names. And it does all the magic behind the scenes for you. So it essentially allows you to implement or use the active record pattern to interact with your data items. So there's a couple of standard functions that you get, like find all, for example, and it's really easy to interact with your data object. Now, if you want to read up a little bit on that, the Quarkus information on that is really good. So they've got all these guides on their website. So there's a nice read up of how to use MongoDB with Panache. I'm not going to repeat everything there. Next, we need to define our REST API. So I've got a simple REST easy definition where we've got essentially a get and a post method that will either return our products or add products even. I've added this host name just so that we can see potentially where this response comes from, which is useful when we want to demo on container platforms. That just refers to a service implementation, which is very straightforward. It just calls the active record list all on a product, and it returns a product listing, which is quite simple. For adding a product, I mean, we're not really using that in this demo, but I've implemented that in any way. It's as simple as stating the field, running a persist, and updating. And that persists your record. The inventory is very similar. There we're using Panache, but in this case we're using the Hibernate version of that because we're now connecting to a relational database in a Postgres. It's a similar way of defining your entity. Once again, there's some nice documentation on how to do Hibernate ORM with Panache. It's got a very similar feel to the Mongo one, so it's really makes your life simple as a developer. That's also got a similar type of API. There are maybe some additional annotations that I'll explain when we get to implement those. It's just a simple REST easy API, so it's a synchronous API. Calling our implementation, that will go find a inventory item by ID. So those are my two basic, simple, bottom level microservices. Now for the actual enrichment service, there is a slight change. So there we are actually combining two different APIs essentially, and then we are using the one to enrich data from the other. Now, unfortunately, there's no nice panache way of doing my models, but yeah, so essentially we modeled a normal POJO, very similar, but now I had to write my getters and setters. Yeah? So that's the only big difference. For my product, the only difference is now I've added some availability information into my product definition. Yeah, so see it as a facade interface, call it that, for my aggregated or enriched data that I want to return. The rest of the application has got a similar structure. We've still got our API service. We've still got our implementation. But in this case, I'm actually routing to a camel implementation. Now, the reason that I'm using camel for a implementation is that it implements a lot of different integration patterns for me out of the box. So this is a typical enrichment pattern. So I wanted to make sure that we actually can choose the nice implementation that works easy for that. Now, Camel Quarkus is also fairly new, so there might be the odd little thing, but I'll mention that a bit later. But essentially, there we've got our main product API that we call. We essentially call our products, retrieve a list of products, and then for each one of the products that we return, we do a call out in parallel to enrich it with the inventory information. That's the high level flow of this API. Now I need to remind you, all this code is available directly on that GitHub. So that's why I'm not going to dive in too much details yet. Yeah? Now with the inventory is very similar, where essentially we just call our availability API and we'll return that response to our enrichment step. Now I have defined some fallback routes already, and this is typically when, in this case, when no products are returned and we need to return some data. So in that case, we just default to a standard product, which is got essentially a unavailable product. Or for the inventory, we default to a 0 availability. Yeah? So that's our fallback that we've defined in this case. Now, what does this look like? So on my machine, I'm running a bunch of local Docker containers. So this is just to simplify my development workflow because, I mean, at the end of the day, we need to think with a developer mindset. So I'm running a MongoDB container. I'm running a Postgres container for my two services that need to persist data. I'm also running some supporting tools like Prometheus. I've got Jaeger running. Yeah, I think that was pretty much that. Yeah. So if we run this, it's fairly simple to run. It's just a Maven Quarkus dev. And this will essentially just launch it on my machine. I'm going to actually run all of them at the same time so that we can see how they are interacting. The catalog. So this is also similar type of thing, but normally when I run more than one instance, we can change our debug ports just so that we don't get conflicts and port clashes and stuff like that. We're running the catalog. Let me start the gateway. Essentially, once all these things are running, we can do a quick sanity check to see if our application is actually returning data. Now, to do that, I normally do a request with Postman. So I've got a selection already, and that just goes and hopefully we don't get our live demo gremlins. No. So that gives me my response back, just to show that we've got a availability information added into our product information now. Now you would see for some of these, you would see a zero availability. This is that fallback method that we are using in case there is no data. And that just keeps our consistency like, well, yes, there's a product, but there's no availability. So it does not break our user experience. Now, before we can actually start with resilience, it makes sense to see what is happening between our microservices. So to see our call stack essentially, or our tracing information for a service. So I think that's the first place I'm going to start, just to show you how simple it is to implement tracing in a service using Quarkus. Now, I'm going to do this on our catalog service. And just for this, I'm going to stop that. So there's a specific Maven target that you can run in order to add in extensions. So in this case, we will just add in our small array implementation of open tracing. And what this would do, essentially, it adds a new dependency in your POM file. So that's, we can actually show you. So in my POM file, that means we've got a new dependency. So nothing prevents you from if you need to do skeletons or something for your project to already include these type of dependencies out of the box. So by doing that already, you've got the ability to see some tracing information in Jaeger. However, what I've found is it's more useful if we can actually inspect what is happening within our class, so that we can see when exceptions are generated in code and our error messages work properly. So to do that, all we need to do is we add an annotation called traced. And we can do that. I normally do that on the API level, but you can also do that on your implementation level. That's it. Fairly simple and straightforward, and maybe just worth showing to you. I've also got some application properties that needs to be configured or to be enabled. And what this would do, it just essentially identifies our service. So what do you want it to be called? It says, well, always take samples of my of the trace. So there are different options for that, but those are the most commonly used ones. And I give it a endpoint way to send the trace information. And in this case, I'm also adding some logging format so that we can actually correlate easily between our traces and our logs. So if we run our request again, let's run that again. And we now go to our Jaeger console. So this is our local instance, our Docker container. We can go and, in this case, we're going to look for our gateway service, but we can see the catalog service is the one that we've added. If we just maybe look at that one for now, we can see it's actually part of a bigger flow trace. Yeah. So what that means is now we can actually see, well, yes, our gateway service is invoked. It does a get all on our products. So there's our product request that was made. And then we actually see a whole bunch of calls to our inventory service, mostly happening in parallel. And then, yeah, so for now, it looks like these ones worked fine. You also see from time to time, it will actually go to a fallback. So this is in this case where we don't have any stock. So this is useful to actually see what is happening in your application. It gives you timing information that you can actually also drill down and see what is taking you long and where. Now, I've actually got an example a little bit later where we will use this to find actually a bug, but let's not say that out loud. Yeah. Okay, so now that we've got tracing in our catalog application, let's add some resilience. If we, for example, had the scenario, and I'm going to simulate that again by disabling the inventory service. If we one of our services are down and we make a call, without resilience, we see some sort of horrible exception being generated. Now, this is typically not something you want your users to see, and yeah, we would rather want to handle this properly. So a simple way of doing that is by adding a circuit breaker with some sort of fallback, which means when a service can go down, we can actually go to a different route. So I've got a little few slides just to show you the concepts on that. So why is this important? Yeah, so we normally code for our happy day scenario where everything works well. However, when one of our dependencies misbehave, that quickly becomes a problem, especially if you think about a traditional web server. There are essentially calling threads that need to make calls to a dependency. Now, if this dependency is down or it takes, worst case scenario, it's slow to respond, we quickly get this situation where all our calling threads are being blocked by one dependency that is misbehaving. Even though the other ones are working fine, eventually our service will be saturated and we won't be able to actually get some data returned. How do we mitigate this? So essentially we want to fail fast with a circuit breaker. So for example, if this service is misbehaving, rather return something from a fallback method. We can also use mechanisms like timeouts to protect our response time. So we have a specific SLA defined, for example, that we can't take longer than 300 milliseconds to respond. And if it takes longer, we time out, essentially. Another approach we could use is something like bulkheads. And what that does, it essentially creates a little thread pool that is used to perform some sort of action, like calling a dependency, for example. And if something gets saturated, the thread pool managed by this bulkhead gets saturated, and the rest of the application still responds fine. So it's similar to a ship, where you actually just close the bulkhead, let that compartment flood, and the rest of the ship can keep sailing. It's also important that we rather return some sort of data from an alternative source when we are failing, instead of just returning an error message. Sometimes it's useful, but typically we would rather want to say, well, if we can't get stock information, rather tell the guy where his closest store is, for example, to go and buy some products. So now, what would that look like in practice? So if we go to our product gateway, so if you remember our dependencies, we've got our product gateway calling our two microservices, our product and inventory service, and one of them are down at the moment. So to do that, Quarkus, and in this case it was Camel Quarkus, also provides a fault tolerance library, also supporting the micro profiles specification for that. I would definitely recommend you to read up on that. There's some nice guides with the fault tolerance, for example. It goes through all the different mechanisms that are available, and it explains it really, really nicely. So it's definitely worth a read. So how do we do this in our Camel application? Once again, we add some extension. So in this case, it's a Camel Quarkus microprofile fault tolerance. Essentially, like we mentioned before, add something to your POM. It will download your Maven things as well. What we would do is, with every call out to external system, so I'm going to do this for both the product and for the inventory, we wrap this essentially in a circuit breaker. So in Camel, it's fairly straightforward. We can do a circuit breaker. I normally indent the block that we can see what's happening. It's just easier to read. And then in case we are actually failing, we also need to define some sort of fallback method. In this case, we're going to keep it simple. We're just going to route to our product fallback route, and we close our block. So essentially what this does, it wraps this in a circuit breaker. And then once, if this fails, it actually just goes to our fallback. Now, this is the most simple form, call it that, of a circuit breaker. It's very similar in feel to a try-catch block. But I mean, there are extra options that you can configure for these circuit breakers. Now, similarly for our inventory, there we're going to do a very similar thing. We're going to add our circuit breaker. And on our fallback, we are going to do some extra things. So I've just going to add some logging messages, essentially, that will tell us that what the exception message is. So why are we falling back, or why are we failing? And also, I want to make sure I can have a log to know when our circuit breaker is actually open. And then once we are falling back, we also just want going to route to our inventory fallback in this case. Once we save, you can see already Quarkus is doing this hot load, which is quite nice. One less command to run, I think. Now, what this does is that on our gateway service now, if we call it, we essentially will now get our response back, even though our inventory service is down. So in this case, it just tells you to go to your local store because we can't find any quantity. Yeah. So that already makes your service a bit more resilient. Yeah, it still responds. It does not generate unnecessary error messages. Now, what is nice in Jaeger, if we go back there, we can now see that some errors happened, which is pretty cool. So we can see in our logs that there was a connection refused. And now we can actually follow exactly what's happening, that yes, connection refused, so we go to our fallback service, for example. So this is what makes this tracing so handy, that you can see what's happening in your application. Now, that's all fair and well, and that's a simple scenario to handle. For me, the most challenging ones would be the ones where a service actually goes and it is really slow to respond. So in this case, we will add some sort of random delay in our service. I'm going to be fairly quick with that. To simulate a service that's not behaving properly. So we are just going to, before we return our inventory, do a random delay. That's right. All this does, it's essentially just lets a thread sleep for up to 3 seconds. Yeah? So it generates some randomness into our application. So if we run this now, we will see that this application will introduce some randomness, yeah? So if we run our application now, we should see that sometimes it takes long. So we can see that almost took 4 seconds, 2.5 seconds. So you can see the performance is generally degraded. Now, what our circuit breaker can do for us is we can now, in our gateway service, on our inventory, we can add some configuration where we say we enable our timeouts and we say, well, timeout after 300 milliseconds. Now, essentially what that would do is after that timeout period is reached, it will go and open the circuit breaker essentially so that you can do your fallback. Now, what's interesting about this is that I did find some sort of issue. So, and I suspect this might be a camel related one, but yeah, like I said, it's a fairly new framework. So we will still work with these guys to sort that out. So what we can see is our application is essentially still taking a long time. However, if we look at our logs, we can see that our circuit breaker is actually open and that timeouts happened. Now, what's interesting is that we can actually pick this up in Jaeger. So if we find our latest trace, something looks strange here because we can actually see that all our calls to the inventory service complete before it goes to the fallback. So in essence, this tells me that the original calling thread is not being interrupted when the timeout happens. So to get around this, it's probably just a temporary workaround, is we could add a socket timeout on our HTTP call to say, well, after our circuit breaker is opened, just time out the socket. And once we do this, it essentially gives us some better performance again. First one, so it's already down to half a second. It's not perfect, but it's already a lot better. Rather have a little bit of degraded performance than one that's really, really long. Now, if we go to our Jaeger trace, we can actually see that we now pick up the proper errors. So now we can see that we actually do get some socket timeouts in this case, and then it goes to our fallback. So we've cut down our execution time quite a bit. Okay, so I think we are running a little bit behind. So when we now want to go and deploy our applications to OpenShift, I'm quickly going to add some metrics and some health checks on our application. This is quite important that we can actually see what our performance is of our services. So with Prometheus and metrics, that we can do potentially dashboards in Grafana, for example. And health checks are also important when we need to know if a container is up and running and needs to be restarted. Now, luckily, this is quite simple in Quarkus. For that, to enable metrics, it's once again a Maven dependency that we add, the small array metrics one. And this already gives you a lot of out-of-the-box metrics for your application. For your health checks, we can just add our health check dependency. And what this does, it gives you a new endpoint in your API that shows you a health status. Let me quickly show that to you. So for that, essentially what that would give you is this type of health check where we can see, yes, it's up. It also gives you the readiness and liveness endpoints for that you normally define on your deployment to a container platform. Also, what we can see is we do get a whole bunch of metrics that are exposed now. You do have the option to go and add custom metrics, like if you want to do timing, for example, on specific functions, it's possible just with the annotation. I mean, there I would also refer you to go and look to the Quarkus documentation for that. They explain that really, really nicely. Now, I think as a last step, let's deploy application to there are quite different of the link to that platform, OpenShift. I mean, you need to check everything that's you well. Again, to deploy to OpenShift, I think it's a unique sort of OpenShift extension that essentially allows you to configure what your different looks like, and you can be using Maven. Personally, I've got a slightly different workflow where I define binary builds, essentially OpenShift. I typically define one for a JVM version or a native version. Then we can, I define my deployments that needs to happen. I need to deploy certain infrastructure. So I've created a set of scripts in this OpenShift branch that you guys can look at. Essentially what this does, there's some scripts to set up some infrastructure like deploying Jaeger, Prometheus, and Grafana. This is just the standalone versions because I don't have admin on this OpenShift cluster. But there's also scripts to deploy our infrastructure. So this just deploys MongoDB instance and a Postgres instance for our microservices from the OpenShift templates. And then I've got another one that actually goes and defines my deployments. So essentially, I do two binary builds. One builds our Docker file with a JVM, and the other one builds our Docker file with a native binary. This allows me to actually control the artifact build on my machine, so I can run a Maven package, for example, and then just upload that artifact and let OpenShift essentially assemble this into a runtime container for me. I also define my deployments. Create a new app on OpenShift. I inject some secret information about the databases that I've provisioned, and then we set our liveness readiness checks, and we can be quite aggressive with our resource limits on our microservices, because Quarkus uses a lot less memory on your environment. Then finally, I just added annotation that our standalone Prometheus can go and scrape metrics. So what this would look like is we can just do let's deploy one of these services. I'll do the catalog one. So what you can do there essentially is that we can do a Maven the package. And we, in this case, I'm just going to skip my tests. Essentially, we do a normal Maven build. It generates, in this case, a jar for me. Now, this compiling goes a lot quicker than the native mode, and this is typically how you would validate as a developer that your code is working. When you are ready, you're happy, you still need to do it in a native build mode so that you can verify that all your code is working in native mode too. There are a couple of issues maybe with reflection. So yeah, you need to test it in native mode before rolling it out. If we then go and start our build, essentially it takes our application jar and that will just push it to our binary build on OpenShift, which would take our artifact and inject it into a runtime container using source to image. Now, while that is running, we can see it's actually just kicking off a Docker build in the background. So while this is running, I just want to show you what this looks like on OpenShift. So essentially what this looks like is that we've got a set of deployment configs for our application. So for each of our microservices, we've got that. You can see we've got some database stores running as well. We've also, what those scripts do, they create some build configs, one for our normal JVM build, one for a native build. And that pushes to our image stream, our containers. What's, I think, just in the, we are running fairly short on time. So just to maybe compare, so we can see our build is actually running there. If we look at the memory consumption maybe on one of these pods, we can see it's really, really low compared to what we've got before. From what I've seen sort of in JVM mode, it was at about 120 megs or so. And when we deploy to native, it's between 60 and 80 megs. That's what I've seen during my experiments. Now for a native build, I'll just show you what the command is. I won't actually run this. Essentially, you need a Graal VM instance on your machine. I'll just paste the commands there. So essentially, you need Graal VM installed. And the only difference is now you've got a P-native option that you actually pass to your build, and that will go and compile and assemble these things. I think just to wrap it up, there are some key takeaways that I want to just mention. So essentially, to recap, a microservice needs to play well in a bigger ecosystem. So make sure that you think about all these capabilities that you need to add around your microservice so that you can manage it consistently and you can observe it consistently. Always plan for failure. Components will go down, containers will die, applications or APIs might become unavailable. Plan for failure and design for that. Don't just leave it up to your developers to figure out what to do. Think about the business case. Think about, well, can we route guys to the closest shop instead of telling them, well, we can't retrieve your stock. For developers, choose frameworks and deployment approaches that ensure the most speed for your developers. There are multiple different ways of doing this. However, I would suggest that developers get their own namespace to test their deployments. They deploy from their machine. And once they are ready to release, then only start using pipelines. In general, pipelines can take a while to execute, and typically a developer wants to test quickly. So always focus on that developer speed. Regarding native builds, it's really resource intensive. There are build limits that you can set. There's a limit that you can set the amount of memory that it consumes on your machine. I had to do that because during builds, it would actually cause my machine to swap and struggle a little bit. So a good limit is normally something like 4 gigabytes, for example, and that just protects your resources on your machine. Developers need to validate their apps work in native mode as well, just because of the way things are assembled during build time. And when we go to a platform like OpenShift or Kubernetes, think maybe about doing dedicated build nodes. So assign some build nodes that can actually deal with the resources on of native builds, and that does not interact or interfere with your normal processing nodes. With native mode, we get smaller runtimes, which is really good. So that means less attack exposure. You can use minimal images for your containers. It uses less resources, and which means that you can improve the container density on your platform. So you can use the resources more efficiently. And it also means quicker scaling. So you can respond easier to and quicker to events that happen. For data persistence, yes, they've got some nice libraries. Panache is a joy to work with. I found it really easy. In general, the framework I felt is really easy to use. So yeah, occasionally there are some bugs, but there is a real active community that resolve issues really, really fast. And now it's also officially supported by Red Hat as part of their application runtimes. There are also some links that you guys can have a look at, most of the things that I've referred to. Yeah. And thanks. That's it from my side.
Wow, it's excellent demonstration, Ben. Really impressive. I hope you guys all enjoyed. We have some questions. We still have some time, right? Yeah. Let's see. Not much. Okay. Vincent has a question, Ben. Were the pods that you showed native builds? Were the pods that you showed in the demo were the native builds?
So yeah, this is for me maybe a restriction of this demo, that native builds take time. So and time is a bit of essence in a demo. So essentially, from what I've seen, if I limit resources to 4 gigabytes for build, it takes about 6 to 10 minutes on my machine to build. So the difference for me, especially when we deploy into OpenShift, well, I would pre-build the binaries and inject it to that binary build, and that bit of injecting it into the container happens a lot quicker because there are way less dependencies that you need to install in your Docker build. So it works essentially in the same way as the JVM deployment. Just the native one, the only difference is essentially that it uses a lot less resources on your environment. So you can maybe be a bit more strict with quotas on your setup, and it will be increased density.
Okay. Another question from Milos. Where do we find the presentation? Well, we will share the presentation and the the video with you after the broadcast. But take some time to how do you call it, save it. So we will notify you when it's ready, and
Yes.
along with the presentation, some extra information. Yeah, guys, any more questions for me or for Ben? Yeah, another one.
What do you consider the closest or alternative competing frameworks of Quarkus? Well, I think there would be a bunch of arguments. I mean, there are alternatives out there. I think the first one that pops up is always Spring Boot. From what I've seen, and I mean, this is just my personal opinion, is that before we've done microservices with Spring Boot, and it works fine. But the startup times really was not that good. So I think this is what also made me excited about this, that it's lightweight, it starts quick, we can scale. But I mean, there are different alternatives as well. Yeah, I mean, something like Micronaut, for example, or those type of things. I would think that that would sort of be the competition.
Yeah, Marcel has a question as well. Can you still do line debugging?
Yes, definitely. Personally, I don't use it that much, but this is that debug flag that I set. Essentially, it creates a port where you can hook into, or the debugger into your application. So you can still set your checkpoints and do that line by line debugging.
Okay. Any more questions, guys? We're still open. Not lunch yet. No. Okay. I think let's finalize it. Guys, I'm very happy we could do this together. I really loved Ben's demo. Excellent. Very good. We will share with you all we have, the video, the presentation, and much more information, all you need. Yeah, and I hope you will join us next time as well. We will plan another one, I think, because there's a lot of things to show and to tell about. And yeah, hope to see you next time.
Yeah, thanks for joining, guys.
Bye-bye.
Bye.